Hallo und herzlich willkommen zur 37. Folge des All-Day Research Podcast, der euch dabei helfen soll, schnell und einfach in die Welt der Forschung einzusteigen. In der heutigen Ausgabe begrüßen wir Professor Dr. Lin Wang. Gemeinsam mit unserem Moderator Marvin Beckmann spricht er über Sustainable IoT Devices. All-Day Research Podcast. Diese Folge des All-Day Research Podcast ist in englischer Sprache aufgezeichnet.
Welcome to the next episode of the All-Day Research Podcast. My name is Marvin Beckmann, and today we will be talking about network efficiency and, for instance, more specifically about sustainable IoT devices and network systems. And for this, I'd like to welcome Professor Dr. Lin Wang. Welcome.
Yeah, thank you very much for having me here. I'm very happy to talk about my research today here. Yeah.
So you're quite new in Paderborn. What was your way to Paderborn? How did you end up here? It's like one of the questions I like to ask at the beginning.
Oh, that's a long story.
We have time.
Yeah, so I basically did my PhD actually back in 2015 in Beijing. And during my PhD, actually, I had an opportunity to visit IMDA Networks, which is actually one of the leading institutions in Europe in my field, right? I spent 1.5 years there. And then during that time, I felt, generally I liked the environment, like especially the research environment in Europe. I thought to come back after my PhD. Then I did it. Basically, the first stop I stayed was in Luxembourg, and it was quite nice there, but I felt the country was a little bit too small for me. So then I moved to Germany. I started like a research leader position in TU Darmstadt. There I spent more than 2 years actually developing quite some projects there. And then after that, I received an offer in Amsterdam for assistant professorship. I went there for 5 years. I thought again, the country was too small for me. So why not coming back? Then I started searching for positions in Germany. And, I was super lucky to get this position in Paderborn, and I'm very happy to be here. And in fact, Paderborn is quite known to me already before I came here because of the research reputation, especially in computer science. So I'm really happy and excited to be here.
You said you started basically your academic journey basically started from your PhD.
Yeah.
In some sense. At some point you probably had to get your first contact with your current research field. When did you have your first contact? When did you in some sense fell in love with your topic?
Yeah, I would say it was the opposite. I felt a little bit tedious with the topic I'm doing now. When I was doing my bachelor studies, actually, I had the computer networks course, which is a very standard offering in the bachelor computer science, right? So at that time, I was doing a practicum for the course where I had to configure some physical devices, and especially I had to dive into the very small details which are usually formed in a sequence of bits, like these different addresses and the different flags and so on, right? I felt quite tedious, figuring out those things. But on the other hand, when you got every detail correct, then everything started to move smoothly. That was really rewarding, right? And then I started my master. During that time, I heard about some quite interesting developments regarding cloud networking. Like cloud computing was picking up, and a lot of people working on how to make cloud networks more performant and at the same time more manageable. And the concept there was basically software-defined networking and how to basically make the networks more programmable. I thought that was a really interesting idea because I had the pain in the bachelor studies, right? And I thought maybe, it's an interesting field for me to explore how to make things easier so other people do not suffer in the future, right? Yeah, so that's why I started looking into this direction for my master's studies, and then I continued with a PhD on that topic.
When you say it was quite tedious in your bachelor's, Do you think going through this experience was still worth it, or would you say just not worth it?
So if I have to comment right now, I would say it is definitely worth it, right? I think it's part of the learning experience, and you have to go through these pains to really understand how things work by actually doing it, right? I mean, in computer systems and computer networking, these kind of practical fields, learning by doing is like a basic philosophy nowadays, right? And I always tell my students right now, if you feel the pain, which is very good, right? Because you are learning.
Yeah, I personally quite enjoyed the computer networks courses from a practical perspective, because whenever you, in some sense, implement something, you always see that it's kind of working at the end. You always have some form of takeaway after these courses. And it's probably the same for you then, right?
Exactly. So typically before you start, you know a clear goal, like at the end, what you can expect, right? And then by figuring out all the details, like very small things, at the end, you will be able to achieve your goal. So that's something really rewarding, right? Very concrete, very specific.
So before we dive deeper into your research field, I'm going to ask you some either-or questions. Just from the top of your mind, say what you prefer. Beer or wine?
Beer.
Mountains or sea?
Mountains, I would say.
Hardware or software?
Software, but with increasing hardware awareness nowadays.
Theory or practice?
Practice.
Data in the cloud or on your own hard drive?
Data in the cloud, because I'm working on cloud computing, and one has to eat their own dog food, right?
Makes sense. Which of the two Mensas do you prefer, the Mensa Forum or the Mensa Academica?
I usually go to the academic.
To the academic, okay.
Yeah.
Coffee or tea?
Coffee.
And lastly, a written or an oral exam?
I would prefer oral exams, and I'm doing that for my courses now. But there are scalability issues, for large courses. So
I heard you have quite a few members in your recent course, right? How many oral exams do you have to do, roughly?
So right now, I'm doing the oral exams for the labs in my course, and I have in total 5 labs throughout the semester. And for every lab, I have this kind of lab groups of 2 students each. And basically, I have initially had around 30-something groups, or even more. I have to do individual interviews with each of them. So it's quite intensive.
Yeah, sounds like a lot. So let's dive into our topic today about your current research. Maybe first start yourself. How would you define your research field? And more specifically, if you would set boundaries on what you yourself do and what you definitely don't want to do and definitely don't do even in your kind of field itself.
Yeah, I would say my current research interest is quite broad in the sense that it concerns different aspects of the subject. But of course, everything in essence will be focused on network systems, right? That's the core of all my topics. So what do we mean by network systems? Basically, any computer system interconnected by a network. This could be like really large-scale data centers, like the cloud data centers everybody uses on a daily basis, right? All to the very small, tiny devices for sensing or for IoT and so on, right? So all these kind of network systems, I care about them. And in particular, I would like to make them more efficient and scalable, and hopefully also more sustainable, like more environment friendly, right? So what I currently do is basically to develop new concepts and methods. And more concretely, we are developing programming models, system software, and also protocols by leveraging the new capabilities enabled by emerging hardware. So we have seen a lot of developments in the hardware world. And how do we leverage those new capabilities provided by them, right, to design better network systems? Yeah. So I would say I'm not constrained to any specific areas right now. So I did actually in the past a little bit theory as well, and I enjoyed that process. But I had the feeling that I would be more energetic when I'm doing more practical things. So that's why I pivoted a little bit to the practical side of my subject, right? And I'm totally fine if we, let's say, touch a little bit the theoretical aspect of the problems we are trying to solve now, which I would feel comfortable as well. Yeah. So I'm not really limited by anything like a clear boundary anywhere.
How does it differ between these two kinds of research? So you said you did theory before and now you do more practice related topics. How does it differ from working on practice and working on theory?
I think people have to have different mindsets, right? I mean, for me, it's more like for the practical things, we have to make like as few assumptions as possible to the problems at hand, right? So we have to start from the very practical constraints of the system, what we should definitely have to follow in order to make it practical and deployable and so on, right? And then we are basically bounded by those constraints and then trying to find solutions, pragmatic solutions within those constraints that can solve the problem, right? And from the theory point of view, the mindset is more like how can we abstract a general problem out of this specific practical issue at hand, right? And then try to find out theoretical approaches, or they call the beauty, right, of the problem or the solution to address this general problem, right, which might be applicable to a wide range of scenarios. So these two are quite different in the way of thinking, I would say.
You basically always already said that something like sustainable IoT devices is also something you're currently working on.
Yeah.
The topic itself has quite some importance going forward. Maybe let's talk a bit more about that. Mm-hmm. Maybe for those hearing about the term IoT for the first time, what does it capture in its essence itself?
So IoT stands for Internet of Things, right? So from the name, you can already guess it's basically trying to build internet for the different objects, like physical objects we have. I mean, the current internet is more for interconnecting people, right? So we are using those devices, and the internet is used for us to pass messages or information across the internet between like individual people, right? But for Internet of Things, it's more like we have some physical devices that will be deployed in places where people easily forget, right? And they have to communicate in order for us to collect information, analyze the environment, and so on. So these kind of networks are typically less obvious to people in their daily life, but they are also very important in many fields like transportation and factories, manufacturing, and so on. So there are a lot of use cases of them as well.
You said that these devices are often deployed in areas where they might be forgotten.
Yeah.
What kind of challenges does this introduce?
So one obvious challenge is the battery on these kind of devices. Usually those devices are quite small in their form factor because they have to be put in a place with kind of space constraints and so on, right? And because of that, usually you use a small battery to power these kind of devices. And once they are deployed, the battery can last for a few months or a couple of years. But then after that, the battery will die, right? And what do we do with that? I mean, if we want the system to sustain, then we have to either replace the battery or recharge the battery. But either way, we will have to involve a lot of human intervention, right? A lot of efforts needed from the management point of view.
If I imagine that I don't want to exchange the battery all the time, so I don't know, I might have a big company and I have like 500 or 5,000 or even more IoT devices deployed. I can't always change the battery. They are not all of them are not plugged in some outlet. What kind of other options can I use? So a first option would be to have some self-sustainability involved, but this probably introduces other problems. Can you take this thought a bit further, maybe?
Yeah, so that's exactly what we are currently exploring in my research group now. So the idea, I mean, of course, we are not the inventor of this idea, right? So basically, we are trying to remove the battery from those devices and power those devices directly from ambient energy. What we call ambient energy is basically the energy existing in the environment, right? For example, the sound vibration, actually we can collect energy from it, right? And also the sunlight and also radio frequency waves, right? All those actually contain energy, but they are really tiny, right? So what we do is we collect those energy from these ambient sources and then store them into a capacitor. Yeah, in the capacitor, we can buffer some energy and then we power the device with the energy we collected and buffered in the capacitor. Yeah, but there are, of course, a lot of challenges with that. I mean, on the one hand, it provides self-sustainability because once you deploy them there, they will just keep collecting energy from the environment and power themselves on automatically, right? You don't have to replace the battery anymore. But on the other hand, the problem is that you don't know when the energy will be available or sufficient to power the device. So that means the device might be turned on for a certain amount of time, but then they have to suffer the power failure and then they have to be recharged. The capacitor has to be recharged until a certain voltage is reached, then the device can be powered on again, right? So that kind of uncertainty and also intermittency is really a challenging for us to build a large-scale IoT system completely out of this kind of devices.
When I think of it, it's also that these capacitors, they are quite limited, and if these IoT devices require large communication, so have to send a lot of messages, it might even be that even within an action they want to perform, they might run out of energy and then have to continue at some other point, right? From
our experience, actually, if you just want to make one contact with another device and then pass, let's say, one message between them, usually the capacitor we are using now are sufficient for that purpose, right? So for passing one message, it's more or less okay, I would say. And then, but the problem is that how do you actually find out, your destination is actually active, right? At the same moment when the current device is active, because for communication to happen, both devices have to be active at the same time, right? And how to keep the connection persistent there. Because if you want to change a lot of messages, then you need a lot of rounds, right? For each round, you can only exchange one message, let's say, right? So that's really a big challenge in there.
When I think of it in terms of scalability, this also introduces quite a range of issues. If I think of making a broadcast, so sending each participant in the network a message, the probability that I randomly get the same time frame, be active in the same time frame as one IoT device is already relatively small. But over time, capturing every IoT device, if it's a big system, not really realistic that I will reach every kind of system at some point.
Yeah.
What can I do, or what kind of ideas have been employed or have you employed to actually make some form of scheduling for these devices?
I mean, as we said, that those devices suffer from sort of a randomness in the availability of energy, right? So as a result of that, they will be turned on and off in a quite random manner. And the challenge is that how to make sure that two devices or more devices are active at the same time so they can communicate, right? A usual way is to just make a random guess. So each of the devices will just randomly guess that, okay, the other device will be active at a certain point. And then I will just delay my own active period so that I can basically, I hope that I can meet the other device at that point, right? If it does not succeed, then you keep repeating until you succeed. So that's a typical approach. But in real world environment, actually, the so-called charging time, because every device has to charge the capacitor, right? The charging time is quite random and varies from device to device. So this approach becomes very inefficient if we have a very dynamic environment and with a lot of devices. So our approach is actually a more structured approach. We argue that, okay, so the problem is actually the lack of certainty in the system. So everything is pretty much random, right? But how can we introduce a little bit certainty into the system so every device could get some common knowledge that can be leveraged to facilitate the communication between those devices, right? So that comes our idea of using maybe one or just a few, very few battery-powered devices among a large number of battery-free devices to actually help the communication. So the idea is that once we introduce this battery-powered device, which is basically follows a fixed working pattern, and other devices can actually easily find it, right? Because it's not random. So we just ask all the battery-free devices to discover first this battery-powered device as the coordinator. And once that is done, the coordinator, the battery-powered device, can disseminate sort of fixed schedules, like fixed time slots, to all the battery-free devices, so that when they try to communicate, they have some sort of rules there to guide their communication pattern, right? So this way, devices can easily know when the other device, when to expect the other device to be active, and then can establish communication. So this is a fundamentally different approach than the random guessing we just talked about before, right? So we introduce this kind of certainty and make sure that the communication is regulated among the battery-free devices, which turns out to be very effective, actually.
What is the overhead of adding such a coordinator to your system? So you said it's only one device in some sense.
Yeah.
But all of the communication that still has to be performed with the coordinator, and so back and forth, and probably for every kind of message I want to send, I need to basically re-ask the coordinator in some sense. If I want to communicate with someone else, I might need new information on when the other person is available. What is the actual overhead of such a coordinator?
Yeah, so there is certainly overhead, but it's not like every time you want to communicate with another device, you have to, ask the coordinator. It's more like at the very beginning when you establish the connection to the coordinator. In that process, you spend time, of course, for that, right? For the establishment of the communication between the device and the coordinator. That takes a little bit of time at the very beginning. But then after that, once all the devices, battery-free devices, have already contacted the coordinator, they know exactly in which time slot any of the other devices would be active with a high probability. Then you just need to try in that kind of time slot, because we basically regulated all the time slots among all the devices, right? So everyone gets a specific slot. So if I get that kind of schedule information from the coordinator, then I can use it to directly contact other devices according to the schedule.
Okay.
Yeah. But there are, of course, problems with that. So this is based on the assumption that every device could maintain some sort of time. So they know that, okay, how long it has been through, and, they need to keep track of the time, right? But that's not always possible, because some of the devices may just have a very serious power failure where the device is completely off. Even the real-time clock is off. Then the device loses the sense of time. Then we have to re-establish this connection to the coordinator and then re-establish this schedule. So this will introduce a lot of overhead in that process.
How is its flexibility? So when I want to add new devices to the system or want to permanently remove some devices, may also be used. What kind of things can I do? I mean, the first thing that comes to my head is restart the coordinator and simply distribute new. Are there other clever ways where we might not have to redistribute all its information and establishment at the beginning, but rather introduce them efficiently? If I have a very large system, this might be more desirable, let's say it this way.
Basically, one way to address that problem is to periodically re-establish a connection to the coordinator. So let's say, for the schedule itself, we have sort of multiple stages of communication, like scheduled communication. And then once that has been done, then we go back to the coordinator communication. So all the devices that had made a contact with the coordinator will have to inform the coordinator again, like what is the current status. If the coordinator misses a signal from a certain device, it can assume that the device is off, right? And then maybe in the next round, the device will join again. So we can basically introduce this kind of periodical checking, heartbeat checking, to make sure that the dynamics of the system are considered in this communication establishment process.
When I think of IoT systems or IoT objects, something that also comes to my mind is that they are quite small. They are not just limited by their capacitor, but also in their general computing power. When I have big computations that still need to be performed, I might not have the computational power to do it fast, but I also might not have maybe even the storage to do all of the computations. What can I generally do from a networking perspective if such a case happens?
Well, for IoT systems, I would say the general or the typical use case is basically sensing, and then you collect a lot of data and then perform some, filtering or some simple computation on the data, and then try to generate some sort of insights from the environment, the surrounding environment, right? So in that perspective, actually, the computation is not that heavy. And for very heavy computations, actually, the typical approach is you collect all the data to a gateway of the network, and then from the gateway, you send it to a data center, let's say, for really heavy computation, right? So for the small computation that need to be done, especially those require real-time responses, you typically do it on the device. But then for the heavy computation that you would require, but not in a real-time fashion, then probably you would do it in the cloud or data center.
If you, in some sense, outsource these computations, so you take them away from the device, from what I've seen, this is also part of your research in some sense, especially in the realm of machine learning and deep learning. Can you maybe say a few words on how these two things tie together, and maybe also where networking comes into play when I look at deep learning itself? I mean, from my first intuition, it's like I have the data. Now there is some deep learning system. I send the data over there and they send me the result back. Yeah. Seems quite easy, but maybe that's not the best thing you can do, probably.
I think this is a very interesting topic. Basically, we are working on a system which is called inference serving system. So the purpose of the system is basically to serving machine learning models for modern applications, right? And what kind of applications we are talking about? I mean, probably everybody has tried ChatGPT, right? Just typing in some text and then send it to the big model and then get some response, right? On the mobile phone, we also have this kind of intelligent assistants like Siri and so on, right? So the typical paradigm is that you send some data and then apply a machine learning model on the data and then get the response back. So the challenge here is how to make it responsive, in the sense that probably you don't want to wait for, a few minutes before you get a response from ChatGPT, right? At the same time, you want the answer you get from the model to be very accurate. So you don't want to get some, very fast response, but then not so accurate or basically useless results, right? So these two are actually conflicting goals, right? So there are basically 3 different approaches you can use to reconcile these 2 goals and design an inference serving system. One way is to basically perform the inference directly on your device, like a mobile phone. So you deploy the machine learning model on the phone, and then every time you get a request, you just apply the computation directly on your device. And on the one hand, the response could be quite fast because you don't have to go through the network. Everything is done locally, right? And also the model is probably optimized for your mobile device. And also you get good privacy, of course, right? So your data would not leave your device. But on the other hand, the results, like the accuracy of the machine learning model may not be that perfect, in the sense that you may get, not so good results, and you find this agent is not so intelligent sometimes, right? So another way would be to deploy the really large models in the cloud. Like nowadays we are talking about LLM, right? So those large language models. So we deploy them in the cloud with a lot of accelerators, like high performance computing units there. And we can actually run those large models very efficiently, very fast there. We can get very accurate results. But the problem is that you have to send your data over the network and then get it back, right? So sending things over the network, over the internet, which does not provide any guarantee, so to say, is sometimes problematic because the network bandwidth can vary and there might be some congestion on the network, right? So that could delay the response to come back to your device. So our idea is, can we leverage the advantages of both platforms, the device and the cloud, and to try to combine them in a harmonic way so that we can exploit the benefits of the two. What is the benefit of the device? We get very fast response, right? But not so accurate result. But from the cloud, we get very accurate result, but not so responsive sometimes. So how can we actually fuse these two approaches and try to come up with a hybrid platform that can, serve inference requests, machine learning requests in a fast and accurate way? So that is one of the topics we are currently exploring.
If you say you're exploring it, what does that mean for me?
So we are trying to find a way to integrate the results from the 2 different platforms in a way so that we can still generate real-time responses on the device, but with the help of the accurate results produced by the cloud. But that is delayed. I mean, it is for the history, right? Because if the result from the cloud comes back 2 or 3 seconds late, probably it's not very useful for the current inference task. It is for the previous one. But how to integrate that kind of delayed results to the current inference request and to make it more accurate, to make the current inference prediction more accurate, that is really a big challenge. And also, we are trying to come up with better protocols for the network so that we can make sure that the response from the cloud will be back by, a certain amount of time limit, right? So how to achieve that? We basically apply some adaptation strategies on the data we send to the cloud and also on the model actually we run on the cloud. So for example, if we know that in the near future the network is going to be very bad, we can actually reduce the quality of the data we send to the cloud. And in the cloud itself, we can try to reduce the size of the model so that we can complete the task much faster. Because we know that we are going to spend more time on the network, right, for the transmission of the data. Then we spend less time on the computation. So that is a way to make a trade-off between these two goals and then make sure that we always meet some sort of time guarantee there.
Does this also correspond to the state of the art currently, or?
Yeah, exactly. So if you look at the recent announcement from Apple, right? So they are doing also this intelligent assistance on their phone and in the new OS. Actually, they announced this kind of hybrid approach where they do partially the inference on the device, but then for the complex inference, actually, they also get the help from their cloud data centers. But apparently for privacy reasons, they inform some encryption on the data and make sure that the data will not be touched by other people, including staff members of Apple and so on. Yeah.
In some sense, you made up quite a few areas we could go in.
Yeah.
And many of them also describe a few challenges that come up with adding these systems. For instance, the privacy factor. What other challenges in your research field are you currently facing? So what are like the big things you seem to make no progress on or are simply very hard to work on?
Yeah. So one thing I have noticed recently is that there is an increasing co-design of software and hardware. So that means there are a lot of innovations from the hardware world, but then in order to leverage the new capabilities enabled by those hardware, you have to develop a new software for them, right? And that is basically the current focus of my research, like leveraging these emerging devices to design better network systems. But the challenge in there is you have to understand how these new devices work. And especially when you are facing a large set of heterogeneous devices with different capabilities, different specifications, the ways you can interact with them, right? It's really challenging, especially for people who do not come from the hardware background, right? So currently we are actually exploring collaborations with our colleagues in the department. For example, I'm exploring a collaboration with Professor Marco Plasner, where he is basically an expert on FPGA, this kind of reconfigurable devices, which have been increasingly exploited in the networking world as well. So right now we are trying to collaborate to see if we can bring those devices in the network domain and develop better software support to integrate them in the network ecosystem.
It almost sounded as if it's taking you back to your bachelor's in some sense. Very tedious work, having to understand the hardware behind it.
Yeah, so that's how things work nowadays, right? So people say that the hardware is the new software. So many innovations come from the hardware world, and then because of that, we have to redo the software stack. And you cannot avoid it by simply ignoring the changes in the hardware, right? If you really want to strive for efficiency, you have to dive into the bottom of things. And basically the hardware would be the starting point for that.
So you said that you're currently exploring collaborations with other people at Paderborn University. How can one get into the field of researching computer networks or networks generally?
I would recommend some basic courses to take to start from, right? So in the bachelor curriculum, I'm teaching the computer networks course, which is definitely recommended if you are interested in networking. But in general, those computer systems courses like operating systems, computer architecture, and also any of the programming courses would be recommended, right? Because computer networking is a practical subject with a lot of programming required. So those are definitely helpful. But at the same time, there are also general readings from, for example, this ACM SIGCOMM community, where they publish general articles about the networking field, like how things are developing and so on. You could follow these kind of articles, right? Sometimes those articles are not hard to read. They are also written for non-experts. So those are a good starting point. And if you want to do some research projects, explore a little bit further. So in my group, we have a lot of openings for thesis projects and also for research assistants, right? So just we have a lot of ideas, more than the pairs of hands we have. So just get in contact and let me know what you are up to.
You've heard it here. So let me get back to the last question.
Sure.
When you're done here, what have you planned for the rest of your day?
I actually have a meeting planned with one of my PhD students. So we just got a paper accepted in a top conference, and we are really excited. Thank you. But we are discussing the artifact evaluation for the paper. So this is a kind of a new process for networking and systems conferences nowadays. So the idea is to make sure that all the results we present in the paper are reproducible. And because of that, we must submit the artifacts, like the software we developed, the scripts, the data we used for the experiments, to a committee for that conference, who will actually check the availability and the completeness of the artifact. Like they are going to run the same scripts we did, and then to see if they can actually generate the figures that appear in the paper, right? So this is really important for practical fields, because making sure the results are reproducible and also the system software is available is the starting point for other people to jump on and then continue from there, right? So we are actually discussing how we can make this process more smooth, and then at the end we want to release everything about the paper. Yeah. In
case you've ever been a reviewer with this new procedure, have you had to run these artifacts, and have you ever faced complications when trying to run artifacts of other submissions?
Yeah, I guess so. So usually, I think this is also an opportunity for students and people who are interested in networking to get into the field, right? Usually, this kind of committee is also open for students. So they get some early experience about networking in general and also how the community works, right? So I would recommend, if you are interested, you can get, try to apply to those committees and get, some involvement into them, right? For me, when I was a PhD student, definitely I did some of these committee works, and sometimes you just get frustrated because you get a lot of programs, all
very well documented,
probably. Code and scripts that are not well documented, and then you have to repeat the process, right? And also there could be a lot of dependencies missing, and so on. So in that sense, you have to get in contact with the authors back and forth, try to understand every detail, and then try your best to reproduce it. But at the end, if it is not reproducible, then you can just stop at an intermediate stage, because there are multiple stages the artifact evaluation can reach, right? So the least, the first stage would be artifact available. So if you just provide the software without being checked, then you also get this kind of badge on the paper, right? If you do all until the end, where let's say the committee believes that the artifact is complete and also all the results are reproducible, then you get all the badges. So that's probably when you read some research papers, you saw this kind of badges. That's basically for this purpose.
Almost seems like some achievement system.
Exactly, yeah. So it's not a mandatory for most conferences, but more and more conferences are kind of encouraging authors to follow this procedure.
Thanks for the insights. That was the All Day Research Podcast, the podcast of the Institute for Computer Science at University Paderborn. My name is Marvin Beckmann, and hopefully we will see or hear each other next time. See you.
Thank you very much. And see you.
All Day Research Podcast. Dies ist ein Projekt in Zusammenarbeit des Instituts für Informatik unter der Leitung von Patricia Höfer und dem Fachschaftsrat Mathematik und Informatik der Universität Paderborn. Moderation und Redaktion Marvin Beckmann. Technik und Redaktion Yannick Greve. Sprecherin Sarah Akopian. Ihnen gefällt der All Day Research Podcast? Dann lassen Sie gerne eine Bewertung da.